So I'm recording this. If you miss part of it or something, or if you know somebody that's going to be away and not getting it, let them know that I'll email everybody, let you know that it's fair game. So we're doing this function here. F of x equals this function, polynomial. The derivative of it, factor out the 3, and then factor it into binomials. You can see that the 8, it's pushing for either 8 and 1 or 4 and 2. Somehow you got to get a 6. It looks like the 4 and the 2 win, and they both got to be negative. In order to get, notice the -4 times -2 gives you positive 8, and you get the sum is -6. So, and now we set this equal to 0 to find our critical points. And notice that the 3 out front, notice that the 3 out front doesn't contribute. That does not matter. That can't influence whether it's 0 or not. The only thing that we got to be concerned about is x minus 4 equals 0 and the x minus 2 equals 0. And therefore x equals 4 and x equals 2. And if we were, now, if you're doing the second derivative test, you don't have to do that first derivative. You could just go from the first derivative up there. I'll start from there in a little bit when I do the second derivative, and just go to the second derivative directly and then answer the question. You can do the thing there. But right now I want to just do a slight review of x equals 2 and x equals 4, what the first derivative test was. Remember that if we're doing a first derivative test, the goal of either test, first derivative or second derivative, is to tell whether you have a local max or a local min. So the first derivative test, it was a matter of picking a point in one of the regions, in each of the regions. An integer, the ones I picked, and the smallest one I could get is the easiest. We could have also picked 0 to the left of 2, and then plug this in. We're trying to see what is the slope like in any of the regions. And the idea is that find out whether it's positive or negative. So I got to plug it into the derivative. I need f prime at 1, f prime at 3, and f prime at 5 to use the first derivative test we're looking for. F prime at 1, I could just plug it back into the original function, and just because it's 1s, it's straightforward. 3 minus 18 plus 24, that's what? 27 minus 18 equals 9. So that's plus 9. So it's a positive sign. So that means it's an increasing function. Slope goes up like that. Then let's plug in 3. Oh, I didn't give much room, did we? Now let's move it down just a little bit. So now we've got f prime at 3. Oh, that's a pretty 3, isn't it? Equals, so we've got, I'll put it into the factored form this time, the derivative. And 3 minus 4 and 3 minus 2. You can see that that's 3 minus 1 plus 1. And we end up with minus 3. So the middle is minus 3, and that's negative. And therefore, the slope is coming down. And you can see that we've got a local max at x equals 2. That's a local max. That's using the first derivative test. And then for f prime at 5, remember, we're picking in the numbers in the region, 3 regions that were determined there. I'll plug that into the factored form again, and we get 5 minus 4 and 5 minus 2 gives me 3, 1, 3, which is 9. So that's plus 9, and that means it is a positive sign, and that means it's looking like this. And that does mean that at x equals 4, we do have a local min, all right? So that first derivative test determined we've got a local max at x equals 2 and a local min at x equals 4. That was the goal. What is it, local max or local min? Now let's go to the second derivative test, all right? Second derivative test was saying that, I'll tell you what, let me go to the text real quick and show you the second derivative test. I'll do that. I will back off from this, new share, go to the book again. And here, the second derivative test, I believe, is a couple pages over. Yeah, there it is. Okay, so if you look at that with me, the second derivative test now, if f prime and f double prime exist on open interval AB, suppose C, a critical number, lies in the range of A to B. It's in that, region. So the critical number that's in there, then if you plug the critical number into the second derivative, and that answer is negative, if it's less than 0, then that means it's concave down, and that means you got a local max. If the second derivative is greater than 0, which means it's positive, which means it's concave up, and therefore f of that critical number has to be a local min because it's concave up. The critical point is going to be at the bottom. So it's a local min, all right? So that's the test. You take the critical point, plug it into the second derivative. So let's do that. I'm going to bring it back to the iPad. All right, so what I'm going to do first is I'm going to write down get the first derivative. I'll bring it down here so it's more present. And this is what you do if you know that what you're trying to do is use the second derivative test. Then you don't need to stop and do the first derivative test and do all that other stuff. You take the first derivative, then take the second derivative. And you get 6x minus 18, which is 6 times x minus 3. So notice what the rule says. Take the critical value, plug it into the second derivative. So the critical values were 2, which gives us 6 times 2 minus 18, which is 12 minus 18, which is minus 6, which is minus, which means it's got a local max because it's negative. That means it's concave down, and therefore the critical value is up at the top. So that's a local max. And f double prime, so this is a local max at x equals 2, right? And f double prime of 4 is 6 times 4 minus 18. 24 minus 18 is positive 6, so it's a positive value. That means it's concave up, and that means the critical point's at the bottom, like we showed here. We showed here that we're at the bottom, and therefore it's a local min. Being positive means it's concave up. That means it looks like this up on the graph here. That means it's a local min. When it was negative, that means it was concave down, and therefore we had a local max. So therefore, that's the general idea of that situation. So local max at x equals 2, local min at x equals 4. And if I asked you for the value, you could plug it in and get it. But that's the idea of the second derivative test, is you take the critical numbers, plug it into the second derivative, and find out if it's concave up or concave down by the plus or minus. Okay? Now, second part of that question, though, one of the questions, what I had asked, was asked is, on what interval is it concave up? On what interval is it concave down? Well, notice this. When we took the second derivative, notice that came down to here. And if we set this equal to 0, we get x minus 3 equals 0. Whoa, off the board. Let's erase that. Sorry about that. I didn't plan that out well. So let's bring this over here. That means x minus 3 must equal 0, so x equals 3. So the value at which the second derivative is made to be equal to 0 has the possibility of being called a special name. Notice it's halfway. I'm going to go back to we're back to the drawing here. 3 is halfway between 4 and 2, and it's where concave down ends and concave up starts. That is precisely what the inflection point is called. So the point of inflection. Let me put this back on the book for a second and show you this definition. That's the second derivative. If we go back one more page, we have this situation going on. Notice the theorem statement up there at the top. A condition for an inflection point. If f denotes a function that is differentiable on an open interval a, b, containing c, period. If c, f of c, is an inflection point, then either the second derivative equals 0 or f double prime, the second derivative is equal to 0 or the second derivative does not exist at c. So in our situation, we've got the place where the second derivative does equal c, and it's where positive and negative, it changes from negative to positive, the second derivative, therefore it is an inflection point. So notice the sequence that they give here, steps for finding an inflection point. Find all numbers where the second derivative is 0 or where the second derivative doesn't exist. Use test of concavity to the right and to the left to determine concavity. So what we did was we picked 2 and 4 and plugged them in, and we got plugged in the 2, we got negative, which means it was concave down, and plugged in the 4 and got concave up, positive. Therefore, if it changes sign from negative to positive, that's indicating that that is an inflection point. So if it changes sign from negative to positive or positive to negative, that's indicating it is a point of inflection or an inflection point, okay? If it doesn't change sign, then there is no inflection point. So it turns out that x equals 3 fits that criteria. Let me go back to the iPad now. All right, and therefore we have a point of inflection. If you're asked about that, the point of inflection occurs at x equals 3. We have an inflection point. And it's because of the fact that when you plugged in 2 and plugged in 4, that the signs changed. Therefore, at 3, we've got a point of inflection, okay? So, any questions on that at all?
I had a quick question on that.
Go ahead, Chase.
So I'm just a tiny bit confused on the very last part where you said f double prime of 2.
Yeah.
That was a -6?
Yes, f double
then,
prime of, yes, that's correct.
And so the -6 means it's concave down, which means it has a local max.
That is right. And that in the head can sometimes get silly, but if you stop and think about it, if it's concave down, then the peak is a max.
Okay, and then the next f double prime 4 was concave down, so local min.
It's positive.
Positive.
So positive, so concave up.
Concave up. Yeah.
And see that the wording doesn't seem to match in a certain sense, but
yeah,
when you draw it out, the concave up means you're at the min.
Okay, and then the number between those two numbers that you tested, if the signs are different, that's the inflection point?
That's the inflection point, and it turns out to be, in this case, that it does change sign from negative to positive, therefore, that place where the second derivative was equal to 0 was at x equals 3, where that happened, that is the possible inflection point, and in our case it is.
Okay, gotcha.
Okay, good. Anything else, anybody? Okay, so let me repeat. If you were just asked to find where is it concave up and where is it concave down, oh, I don't think we said that, did we? No, we didn't. On what interval is it concave up and concave down? So if you ever ask that, you don't have to do the first derivative test to do that. If you're being asked for concavity, then just go straight to the second derivative and answer the question. That's it. But let's denote what the interval is on which it's concave down. So you notice that the point of inflection is where the concave downness stops. So it stops here at x equals 3. Therefore, everything to the left is concave down. So it would be, so pardon me, this is getting mashed together here. It would be concave down on the interval negative infinity up to 3, not including 3, because 3 is not down or up. It's the in-between moment. So it would end up being that. And concave up is over here. It starts at 3 and comes over here on this side. So it is concave up on 3 to positive infinity. Okay, let me go ahead and clear out that notation back there. So it ends up being concave up on 3 to positive infinity. I think you can see that all the way to the right, it's going up forever. So that's concave up, but they're coming back this way. When you get to the point of inflection, it stops. So it doesn't include 3, but so it's open interval at 3 and open interval at 3 on this end. Okay, any questions on that? Okay, there's a few questions I've asked you on Sapling to go in and do. Please try them. I think there's 10 from section 4.4, and feel free to do them. I'm going to open your mic up. Just let me make sure everybody's
one question.
Okay, I hear a question being asked.
So will you ever, can you hear me?
Yes, I got you open now. What's up? Who is?
This is Tyler.
Okay, good. What do you have?
Will there ever be a question where you're just asking for the point of inflection?
The point of inflection, okay? So you would go in and take the second derivative and see if there's any numbers that make it equal to 0. And if there is a number, in our case it was 3, made it 0, you check to the right and check to the left and see if it changes sign on the second derivative, if the second derivative changes sign. Because in order to be a point of inflection, it's got to go from negative to positive or positive to negative. And if it doesn't do that, then it's not a point of inflection.
Okay.
All right?
I got another quick question too.
Go ahead, Chase.
So when we're doing the second derivative test, do we first have to make sure we find the critical points from the first? Okay.
Yeah, because part of this definition is that what we did down here, down the bottom right corner of this, let me call that back up. When we got into down the iPad here, the bottom right corner here, that we got the second derivative. We got the second derivative and plugged in the critical value, the critical point, the critical x into the second derivative. And that was where we determined whether the second derivative was positive or negative.
Okay, and you always have to find that from the first derivative test.
Well, it's not the first derivative test, but from the first derivative.
This setting it equal to 0. Gotcha.
So all you do is take the first derivative, factor it, find the critical numbers are at 2 and 4. Therefore, take the second derivative and plug 2 and 4 into the second derivative and see if they're plus or minus. That's it.
Perfect.
So in Sapling, that should be cool. All right, tell you what, I want to try and get through the other stuff. So let me go on to L'Hopital. One of the things that is a requirement of talking about L'Hopital's rule is that indeterminate forms are an important part of the situation, and there are particular indeterminate forms that are needed in order to use L'Hopital's rule. So let me put the camera on the book again just for a second. And point out that this box here is describing, it's using the term, it's called indeterminate because like it's a situation where you've got a limit and you can't determine what the limit is because there's got a situation that when you plug in C into this function, it's a rational function. It's got a function on top and a function on the bottom. You plug in C and you get 0 out of 0. Hold on a second. My camera is losing focus. Okay, so that when you plug in C, you get 0 over 0. It's not a number. There's not an answer to the question, or it's not going to infinity, or it's not going to 0, or whatever. It's going to 0 over 0. And if it's 0 over 0, or if it's going to infinity over infinity, those are cues that you can use L'Hopital's rule. And let me give you a sense of, so the idea is find the limit in the numerator and find the limit of the denominator. And if you get 0 over 0 or infinity over infinity, then you can use L'Hopital's rule, which is a special kind of a situation, which says this, Now, this is kind of wordy and it's a little backwards in wording, I think. But the idea is that if you've got a situation where you've got a rational function and you're taking the limit as it goes to some value c, then if you get 0 over 0, or where's it going? Hold on, where are you going? Okay, it's sliding down. What are you doing? Okay, I'm talking to the tripod stand. Hang on one second. Okay, here we go. Here we go. It's moving down. Oh, this is what's moving. There we go. Okay, so now the situation is this. The wording again is a little clumsy, I think, but what it's saying is that the last sentence is the key. First of all, it's got to be a rational function, and it's got to be going to 0 over 0 or infinity over infinity. It's saying that if that is true, then take the derivative of the top and take the derivative of the bottom. And that limit will be the same as if before you took the derivative. That's what that's saying. So if you have a situation that's 0 over 0 or infinity over infinity, then take the derivative of the top and take the derivative of the bottom and recheck the limit, and that will be your answer to the original question. So you don't use the quotient rule. You take the derivative of the top. Notice that's f prime on top and g prime on the bottom. So that's not the quotient rule. You take the derivative of each. I got a couple of examples here I'd like to do. Yeah, the camera just died. Okay, so hang on a second. I'm going to go to the iPad again here. Let's go to a new share and go to iPad. Okay, so a couple of problems that I'd like to look at are that represent L'Hopital's rule. The first one is we get a 0 over 0. All right, and that is, let's look at this one. So if we've got the limit as x goes to 2 of x squared minus 4 over x minus 2, you can see right now that if I just place 2 in there, I get, so I don't need limit because I'm placing the 2 in, I get 4 minus 4 over 2 minus 2, which is 0 over 0. And really what I've typically done in my case, and for you guys too, if you're in an assessment or something, you can just write that up above. So in other words, write it up here, do a little up here. You get 4 minus 4 over 2 minus 2 equals 0 over 0. That verifies that you can use L'Hopital's rule. You need to do that. If that doesn't happen, then L'Hopital's rule isn't appropriate, okay? So part of a correct answer to the problem is that you verified that it's L'Hopital's rule is appropriate by taking it to 0 over 0 or infinity over infinity. So since it does go to 0 over 0, we can use L'Hopital's rule, which says if I take the derivative of the top and the derivative of the bottom, I can do the same limit. And therefore, the derivative of the top is 2x, and the derivative of the bottom is 1. So now we've got the limit as x goes to 2. That's equal to 2 times 2, which is 4. That is the limit. And that was the original limit too. And if you do it on a graph, like I do it on Desmos, you'll see that that's what that function is at that point. Tell you what, I'm not going to go there right now. I want to stay with this. I want to make sure we get through the 4-7 stuff too. Let's do another one. That's not quite as automatic, okay? See, what we could have done on this problem too, remember that this is factorable, and we could have gone another way to find that the limit was 4, because we could have made this x minus 2 times x plus 2, difference of 2 squares, over x minus 2, and cancel, and we're left with the limit as x goes to 2 of x plus 2. And that is equal to 2 plus 2, which is 4. So you get 4 both times, but if you have a factoring situation, you can do that and get the answer in the other way. But there's some time, or you could have used L'Hopital's rule. But there's sometimes when you can't do factoring. So for instance, look at this one. Limit as x goes to 0 of e to the 2x minus 1 over x. And part of the situation here is that the limit is, let's just plug it in and see what we get. We can't factor it, we can't simplify it. So I'm just gonna plug in 0. That means I don't need lim now. So I'm just plugging in 0. So I've got e to the 2 times 0 is 0 minus 1 over 0 gives me 1 minus 1 over 0, which is 0 over 0. That verifies I can use L'Hopital's rule, okay? So I start with limit as x goes to 0 of e to the 2x minus 1 over x. And now to use L'Hopital's rule, I take the derivative of the top and the derivative of the bottom. So I take the derivative of the bottom for, that is going to be equal to, so I need the lim. Notice that, I gotta catch that. I'm taking the limit of the derivative. The limit's a part of the correct answer. If you don't include limit, it's not gonna be a correct statement, okay? You'll see why in a second. The limit as x goes to 0, the denominator becomes 1. And now, e to the 2x, that means that's e to the u. And the derivative of e to the u is e to the u du. So we get e to the u back times the derivative of that u. So we get e to the u back times the derivative of u, which is derivative of 2x is 2. So I'll just put that in front. And the derivative of minus 1 is 0. So we end up with the limit as x goes to 0 of 2 e to the 2x. And as x goes to 0 there, what do we get? We get that's equal to 2 times e to the 0, 2 times 1, which is 2. Question?
Hold on.
Okay. Okay, tell you what. All right, good. Okay, so I've muted it now. I can't hear you if you're talking. I'll ask questions in again in just a minute. So the answer to that question is 2. The limit is 2 in that moment. Okay, now, anybody have a question on that?
Yeah.
Larry,
Could you write out
Cameron,
could
Go
you
ahead.
write out the D to the U part?
no. Summer, who has to run her phone? Who has to run her phone?
Okay. Okay, I'm going to mute the situation again. All right, so let me show you one more situation, you guys. It's kind of an important one, and it has to do with, I'm going to go back to the iPad again. It has to do with the fact that sometimes you might have to use L'Hopital's rule twice. So for instance, let me show you another one here. Come on. Oh, here we go. So if we had the limit as x goes to infinity, let's do first x over e to the x. We haven't done one for infinity yet. Again, typically we don't substitute in infinity. Infinity is not a number. But as x goes to infinity, x is going to infinity, right? And e to the x is getting huge, it's going to infinity. So that means we've got infinity over infinity. And as a result, we end up with then infinity over infinity. That means you can use L'Hopital's rule. So let's go back to limit of as x goes to infinity of x over e to the x. We end up with, take the derivative of the top, and I get 1, and the derivative of e to the x is e to the x. And now as x goes to infinity, the top is 1, and the bottom gets huge, which means this is going to 0. All right? That is a straightforward infinity problem. Now look at this one now. This is kind of important because sometimes you have to do it twice. Here's an example where you've got to do it twice. The limit as x goes to infinity of x squared over e to the x. All right? Which is equal to, okay, so I plug in infinity. You can see it's going to be infinity over infinity again. So that means I can use L'Hopital's rule. But the idea is now if I take the derivative of the top, and the lim's got to be there, it's part of a correct solution, I get 2x on top over e to the x. Now I still get infinity over infinity, so I've got to do it again. That means you keep doing it until you don't get the indeterminate form, okay? So that means now we get lim as x goes to infinity of 2 over e to the x. And now the top stays fixed and the bottom gets huge, and that means it's going again to 0. You know, notice it's also kind of interesting that this is twice as big as this, and yet they both go to 0, you know? That's kind of interesting. That's kind of a special moment. But the idea is that this thing is going, as you go to infinity, that 2 becomes nothing. You're going to 0. Questions on that at all now? Let me unmute you. Let me unmute. And, okay, your mic is open. If you're locked, it's on your end. So anybody have any questions there?
I got a quick question on what we just did there. The
Okay.
So what you were doing when you had to do the rule twice was basically taking the derivative twice. So you took it, x squared goes to 2x, then it goes to 2.
Right.
Because
So, but make sure we just do one step at a time. So x squared goes to 2x, and e to the x goes to e to the x. And then, yeah, 2x goes to 2, and e to the x goes to e to the x.
okay,
That's exactly right.
got it.
Okay, tell you what, that's L'Hopital. So for section 4.5, I think I got 6 or 8 problems in there. There's a variety of different kinds. Make sure you check first 0 over 0 or infinity over infinity. You go
They
from
took them out because they want y'all to stay 2 big buggies distance apart. They took them out because their gist is they want y'all to stay the distance of 2 big buggies apart. Because
I'm
that's
going to mute the
right there around 6 feet.
answer. Okay, so one last thing I
I'm
want to
sure that's part of it too.
One last thing I want to do is the problem from 4.7, okay? So let's go there. I want to show you what we're talking about in 4.7. It is the optimization problems. I've been talking about this a little bit. This is kind of a cool part of the taking the derivative stuff and using it to answer questions that are real life stuff. It's kind of cool. Here is the sequence of events. Well, tell you what, let's just run through a problem first. And now I'll show you a problem that matches optimization and what the idea of it is. And then we'll go through the steps that they give in the text, okay? So here, I had a different book that has a couple of simple problems in it that I think are most clear. Let me do this. So I'm going to share screen, look at the book. All right, and we're going to look at down here. Looks like the camera's tilted. And I'm going to drop it down a little bit, build it up so you can see a little better. Numbers 1 and 2 are what I'm talking about here. Okay, numbers 1 and 2. And pardon me if it's on a slant, I'll try to straighten it up a little and get that 4, 3. This is out of a different book, so it's a different section. But here's the deal. So you've got 2 non-negative numbers and the sum is 100. What is the maximum value of the product of these 2 numbers? Okay, so part of the situation, what we're doing when you're doing an optimization problem, you have 2 different equations involved in solving the problem, okay? So in our situation right here, I'm going to go to the iPad now, get a gist of this. And the second one, maybe I'll do tomorrow as a practice problem, okay? But the first one is the sum of 2 numbers, non-negative numbers, is 100. What's the maximum value of the product of these 2 numbers, okay? So have that in your head, and then I'm going to go over to my iPad. And let's do that. Okay, so the sum of 2 numbers was 100, right? So 2 numbers. So we've got 2 equations. We've got a sum, and there's 2 numbers added together. And we could call that S because we're going to want to give it a variable name. A variable name, so we'll call it S. And then we've got a product of those same 2 numbers, X and Y. So product equals X times Y. And we're given that the sum is equal to 100. So it turns out in this case, we've got X plus Y equals 100. This is the characteristic of an optimization problem. You've got 2 formulas. You're given a constraint on one of them. One of them is set. X plus Y is 100. Maximize or minimize the other one. That's an optimization problem. You're trying to optimize this product. It's a maximum. We're trying to maximize it. So what we've got to do though, we've got the product function. We can call it P equals XY, but notice that it's in terms of X and Y. So what we can do is go to the constraint equation, solve for one of the letters, substitute it into the other equation, and you'll just have X's. And that means you can take the derivative and set it equal to 0. That's the idea, okay? So this problem up here, the sum, let's solve for y. Y equals subtract x, all right? And now if we substitute that in here, we end up with P equals X times 100 minus X. This is the optimization. Solve for one variable in the one that you had the constraint on, substitute it in, and now this can be written P of X. There's a one variable. So this becomes 100x minus x squared. Okay? So it says maximize the product. Notice what the shape of this graph is, of this function. It's a parabola, right? Upside down parabola. It's got a max. The answer is going to happen at the top there. That's where we set the derivative. In fact, find the derivative and set it equal to 0. That's the slope. Where is the slope equal to 0? That's the derivative when it's equal to 0. So we take the derivative, set it equal to 0, and we end up with, it happens at x equals 50. And one thing that happens many times is somebody will say, yes, I solved for x, I got my answer. No, the question is, what's the maximum product? So you got to go back in several times. Like right now, we could go back into our P function where we've substituted in and plug in 50 and get the answer. That would answer the question. There's a lot of times when it's more involved than that, and solving for y would be a pertinent part of doing the problem, because that would answer some other questions possibly. So let's do that. So remember, somewhere along the way, you had to solve for y in order to get it to be all in terms of x. So I'm going to we're going to solve for y here. We got y equals 100 minus 50, which is 50. So we've got y equals 50. We've got x equals 50. And now we can answer the question. P equals 50 times 50, 2,500. And that means maximum product. Remember to go back and answer the question. Maximum product is 2,500. And notice that if we had gone back here and plugged in 50 here, it would be 50 times 50, 50 out here and 50 there. That would have given us 2,500. Or 50 here gives us 5,000 minus 2,500. Either way, but the max product is 2,500. So the situation, you guys, is that is an optimization problem. Two equations, boom. Given a constraint on one of them, asked to maximize the other or minimize. Therefore, substitute in, get it to be in terms of one variable, take the derivative, set it equal to 0. That's going to be the pattern for all of them. There's some kind of interesting problems, I think, if you get into them in section 4 or 7. Take a shot at those and come in tomorrow or Wednesday with questions, and I'll gladly handle them and clarify things that you've got. I've really trimmed down. I've trimmed down the number of problems that you had because of the fact there were several that were just clumsy, okay? And I can't get rid of this sign into iTunes thing. But anyway, the situation there is try the problems, come in with questions, and be ready for a light quiz on Thursday, okay? I probably will do a L'Hopital rule later on the test. We got limitations on what we can do on the quiz. So I'm going to keep it simple. I'm not sure what I'm doing yet, but plan on taking a quiz on Thursday. I'll update you as the date gets closer. And then we'll have a test a little bit down the road where L'Hopital will show up then. But practice L'Hopital, get down 4.5, But the other problems are going to be more likely on the quiz on Thursday. Okay? Take a shot at them. I've moved chapter 3 questions out also due to the end of the week. So I hope you can smile about that too if you haven't gotten those done. Any more questions at all?
Is there an opportunity tomorrow? Are you doing a Zoom session tomorrow or just Wednesday?
So tomorrow is going to be office hours. So during
Okay.
class time or 2 to 3.
Perfect.
And Wednesday and Thursday also.
Okay.
But I'll be here at class time and during office hours. So check in. Again, that's at the top of the top box, up in the first box, and you as you learn. That Zoom link at the top. I'll send a reminder out.
Perfect.
Anybody else have anything else? Any questions? Or do you have any questions, Chase? All right. Well, be well, you guys, and I hope to see you. We'll see you a little bit later sometime this week. Bye-bye.
Bye, Dr. Bob.
Yep.
Blake, got any questions at all?
No, I'm good. I'm just looking over the notes.
Okay, good, good. Take your time. I'm going to have a recording of this up in just a little bit. It takes a few minutes for the data to transfer, but you can look at it again if it went by too quickly.
Okay, no, you're good. Thank you.
Okay, good.